Okay, distance between a point and a line in R3. They've given us our point, which is great. Makes that part easy, but our equation is not in Cartesian form. Okay, so what we're going to do is we're going to put it into our parametric form, and that way we can find another point. We have one point on the line. Okay, we're going to need to find another point so that we can find something perpendicular to these two vectors. So in order to find another point, I'm going to put it into parametric form. So x is equal to 1, y is equal to, what do we got here? 2 plus t, and z is equal to -1 plus t. Okay? So what we're going to do is we're just going to choose an arbitrary t value, and that way we can find what the rest of our things are going to be. So let's say we have t is equal to the number 1. Well, x will still equal 1. Y will then equal 2 plus 1, which is 3. Okay, so let's say we're putting our coordinate together, 1, 3, and z is equal to -1 plus 1, which is 0. So our other coordinate is 1, 3, 0, and our first coordinate is 1, 2, -1. Now remember, these are two vectors in a sense. So these two vectors, to find something perpendicular to the two of them, they'll make up a plane. If we find something perpendicular to the two of them, we'll get the normal from this vector itself, and the normal will help us put it into the Cartesian form. So these 2 points here, we'll call them, remember this is our point Q. If you guys remember, we talked about point P and Q. This is our point Q right now. So we're trying to find QP in space. Our point QP here in space, yes, we could have done it that way. Oh, they chose the other way. This is fine. The way the book did it is it actually used point P and Q. We didn't actually have to find another point. That was my mistake. Because they had 2 points, and this could have been point Q. That's okay. We found another point along the line. Either of these would be acceptable. You could use this point or this point. They both happen to be on the line. I ended up giving us a lot of extra work for nothing. They've already given us a point. Should have recognized that. So, because we have this point here, we'll go with what they have. Their PQ is essentially their other vector they're trying to find. So their other vector they're trying to find here is, we'll call this our Q also. Either of these could represent Q. And when finding that vector, we'll call this our second coordinate, and this is our first coordinate. So we take x2 minus x1, which would give us 1 subtract -1. y2 minus y1 gives us 2 minus 1. And z2, which is -1, minus z1, which is 6. So our new vector is 2, 1, -7. Okay? So think of that as it's in space. We're on some line here. This is our point P, which is -1, 1, and 6. Okay? Our point Q is somewhere on the line. We chose 1, 2, and -1. We are now creating a vector. That's what our QP is. We've created vector QP, and we need to find the distance from this point to the line, which is going to be a right angle. So if you guys remember, this is the idea of a scalar projection. A scalar projection is finding the distance here. The only difference is we're finding this distance when normally our scalar projections would find this distance here. Okay? It's still setting up the same idea. Now, we have a formula for this one. And we also need to find, because we have our projection vector here, this is what this line is traveling at. Okay? And because that line is traveling at this, and our QP is around this direction, we need to find a right angle from those two vectors, all right, to find this point in 3 space. So we're going to find the cross product of the two of them. So we're finding the cross product of our direction vector, which was originally 0, 1, 1. And our new QP, which is, what do we get? 2, 1, and negative 7. Okay? So essentially this is our QP, and this is our M, you could say. This is important because if you guys remember our formula, it's the absolute value of M cross. So we have our direction vector. We now have our QP, cross QP, divided by our M. Okay? So we found our QP, which is our goal, and we have our M. We're finding the cross products, which is going to be the top part of this formula. And then we're just going to find the absolute value of vector M, and that will be the bottom part of the formula. So when we go through this, our top part is going to give us A2 times B3 gives us negative 7. Negative 7. Our next part here, we're subtracting. A2 B3, B2 A3 minus 1. Then we have A3 times B1, which is 2. Subtract A1 times B3, which is 0. And A1 times B2, which is 0. Subtract A2 times B1, which is the number 2. Okay. And remember, we're going to find the absolute value of this eventually. So this is going to give us our coordinate, which is going to be at negative 8, 2, and negative 2. Okay. So that was our M cross QP. We're going to plug this into our formula. Now remember, to find the absolute value of a coordinate, we put it into our formula a squared, b squared, c squared. So what's going to happen when we put it into our distance formula, looking for the absolute value of that coordinate M cross QP, we're left with the root of negative 8 squared plus 2 squared plus negative 2 squared divided by, and we're looking for the absolute value of M. Well, it's the same as above, just different numbers. The root of 0 squared plus 1 squared plus 1 squared. So let's bring this to the forefront now. D is equal to the square root of 64 plus 8, 52. Nope, 72. Why did I say 52? Divided by 0 squared, 0. 1 plus 1 is 2. So root 2. So our distance here, oh, they've broken it all up. They've broken our 72 into 6 root 2. Essentially, you can just put this straight into your calculator because we are just looking for a multiple. I didn't say I wanted it in radical form. So let's say we just had 72 rooted divided by the root of 2, 6. So our value ends up being 6.